Dear students, well, this is another chapter that I felt like a recording for you since we may not get many days of class, and I thought like recording would really give you that convenience of going through as and when you have time. So today I have chosen a very interesting topic. The name of the topic is chemical thermodynamics. Now, this chapter is from section 1. It's chapter number 4. You must have heard this word thermodynamics in physics. This word you'll find at many places. Basically, thermo means heat. So anything that involves heat would come under the science of thermodynamics. So what is thermodynamics? Thermodynamics is a branch of science which deals with the different forms of energy, the quantitative relationships between them, and the energy changes that occur in physical and chemical processes. So that's the definition of a general term like thermodynamics. Since we are chemistry students, we'll be not looking at thermodynamics which is relatable to physics, we'll be looking at chemical thermodynamics. Now, what is chemical thermodynamics? It deals with energy changes accompanying chemical transformation. So when I say chemical transformation, what do I mean? I mean chemical reactions, because a chemical reaction brings about transformation in those reactants to form products. No? So chemical thermodynamics is something that deals with energy changes accompanying chemical transformation. Now there are two important terms that we'll be looking at in this chapter, that is system and surroundings. Now what is system and what is surrounding? System and surroundings together is called universe. Now what is system? System, it is part of universe under thermodynamic study, and surroundings is all other parts of the universe outside the system. Now you would be wondering what this system and surrounding exactly is. I'll give an example, my dear students. The example is of a beaker containing water. Now suppose if I keep a beaker containing water on a table, that beaker containing water becomes my system, and everything around it becomes surroundings. Both the system and the surrounding together, what do I call it? I call it as universe. Similarly, if I'm performing an experiment containing a test tube, in that test tube I put reactant A and reactant B for a reaction to take place. So the contents in that test tube becomes my system, and everything around the test tube, when I say around the test tube, means the conditions of the surrounding, like the temperature, the pressure, which will affect the system, that would come under surroundings. Both the system and the surroundings, that is the test tube, the reaction and the surrounding together, I'll call it as universe. I hope you've understood the meaning of system and surroundings. I'll give you one more example to make things more simpler. For example, if you are standing on the floor, you become the system and everything around it becomes a surrounding. So you become part of the universe. You become part of the universe under thermodynamic study. Now, why under thermodynamic study? Because if you're standing, automatically the temperature in the surrounding is affecting your body. If the weather is cold in the surrounding, definitely it's going to affect the system, that is you. If the weather is hot, automatically you'll start sweating. That means it has affected the system, right? I'm sure you've understood the meaning of system and surroundings. Let us look at the different types of system. Types of system is what we're going to look at now. The first type of system is open system. Now in this, exchange of heat and matter takes place For example, a hot cup of tea with no lid. Imagine you're holding a cup of tea which is hot, which has no lid, which means heat and matter both will move out of that cup of tea. Heat, of course, after some time, what will happen is it will start becoming cold. No, that's how exchange of heat will take place. So surrounding, whatever the heat is in the surrounding, that will come to that cup of tea. And the matter is also passed on to the surroundings. Why? Because when the tea is evaporating, the contents in the tea, the liquid is evaporating, what is happening is the matter present in it is also disappearing. Okay, so such a system is called as open system. Now, what is closed system? In this, only exchange of heat takes place. Exchange of matter doesn't take place. Only exchange of heat takes place. Now, for example, a hot cup of tea with lid. Remember, in earlier this thing, it was with no lid, but here it is covered with lid. So in that matter, if it evaporates, it will hit the lid and come back and fall in the cup of tea. No? So there'll be only exchange of heat, which means after some period of time, even if the cup is covered with a lid, still there will be exchange of heat. I'm sure you must have observed that no matter how much ever you cover it, after some time it does become cold. That means exchange of heat has taken place. The third type of system is called as isolated system. Now in this, exchange of both heat and matter does not take place. For example, thermos flask. Now, why do we use thermos flask? So that whatever is there in that thermos, it remains in that same temperature. Suppose if I keep hot cup of tea, hot tea, not cup of tea. So if I pour the contents of this hot cup of tea in thermos flask, why do I do that? So that there is no exchange of heat, so that that hot remains hot. Okay, and of course, since thermos flask is covered, there will be no exchange of matter. Next is properties of a system. Now, what are the properties? There are two types of properties. One is extensive property and the other one is intensive property. In extensive property, properties dependent on magnitude of a substance. Now, example, mass and volume. Okay, so magnitude. For example, if I say 10 grams, 20 grams, so what am I changing? The number. No, so 10, 20, 30. Okay, so that becomes extensive property. Intensive property means properties not dependent on magnitude of a substance. Example, boiling point, melting point, temperature, density. To give you an example, melting point of a 10-gram ice, okay, melting point of a 10-gram ice will not change if I take 100 grams of ice. Okay, similarly, boiling point of water, okay, water boils at 100 degrees Celsius. No, so boiling point of water, whether I take 10 ml water or 100 ml water, magnitude doesn't matter, it's not dependent. No, whether I take 10 ml water or 100 ml water, boiling point of water will always be 100 degrees Celsius. That's the meaning of intensive property. In extensive property, you know it very well, 1 kilogram of sugar and 10 kilogram of sugar, they are different. By what? By mass or by weight. No, so that is called as extensive property, wherein the magnitude plays an important role. Here there is no dependence on magnitude, so the number doesn't matter. Whether I take 10 ml water or 100 ml water, the boiling point will remain same. So such kind of properties are called as intensive properties. In the previous video, my dear students, we looked at types of system and properties of system. So in types of system, we saw open system, closed system, and isolated system. And in properties of system, we looked at extensive and intensive property. Now let's take a look at something that's very, very important in this chapter, an expression for pressure volume work. Now, whenever we talk about any reaction, since we are doing chemical thermodynamics, so there are heat exchanges taking place whenever a reaction occurs. So when reaction occurs or there is exchange of heat, needless to say, there is some kind of work that is done. Okay. Now, what do we know about work? Work is product of force and displacement. Now you must have seen in physics W is equal to F into S, where F is the symbol of force and S is the symbol of displacement. Why is it not D? Because D is used for distance. And you know it, there is a difference between distance and displacement. So what is work? Is the product of force and displacement. Now, if the force applied is in the opposite direction, the sign convention changes. Okay, so if the force applied is in the opposite direction, you must have seen a piston. A piston is something that we use maybe while filling air in cycle tires. You all must have seen at cycle shops, the way they pump air, no, in the cycle tires. So when the piston goes up, what happens is you're pushing air into the tire through the pipe, and when that piston comes up, okay, that's the time wherein you're filling air in that cylinder, no, that cylindrical pump. So that's exactly what happens. So then what happens is W is equal to, now here since I'm talking about displacement and not distance, I'm taking it as D, okay, instead of S. No, S is taken when in the same concept, in the same chapter, there is distance and displacement that's been spoken about. So in this chapter, since we're not going to look at distance at all, let's keep it simple. We'll call displacement as D. So W is equal to product of F into D becomes minus F into D. No, because the force applied is in the opposite direction. So instead of plus, it becomes minus. Now, what do I know about force? Force is the product of pressure and area. That's the definition of force. It's nothing but the pressure multiplied by the area. And if I substitute this value in this equation here, so W becomes minus P into A into D. Okay, so minus P into A is that minus F into D, right? Now, what is that pressure? Pressure is when I'm expanding it, when I'm taking the piston up, okay, in the opposite direction. So W becomes, my work done becomes minus P into V2 minus V1. Now what is V2 minus V1? That's delta V, difference in volume. No? So difference in volume is nothing but A into D. What is A into D? Area into displacement. Area into displacement means what? Area is calculated in meter square, distance in meter. So meter square into meter becomes meter cube. Now meter cube is a unit of which quantity? Volume, isn't it? So this can be replaced with volume. Now since volume is nothing but difference in volume, I'll take you back to that action of piston. When the piston comes up, volume becomes more. When the piston is pushed down, volume of the gas in that cylinder reduces. So initially if it is V2, later it becomes V1, no, because the volume of air, volume of gas in the cylinder changes. So that's how I get delta V as V2 minus V1. So can I write down like this? Minus Pex delta V? Yes, I can. So this is an expression for pressure volume work. Very, very important expression. That's why I've put that in bold. Q is equal to minus Px delta V, where delta V is change in volume and minus Px is pressure when gas is expanded and not contracted. Okay.